It's section 8.4 today. Today we're going to put logarithms and exponents all together, and we're going to actually learn how to solve logarithmic and exponential equations. Okay. Once again, I'm going to split this up into two parts, just because I don't want you to watch a 2-hour-long video. Not that this one's going to be an hour, but nonetheless, I want to separate this into two sections. Okay? Now, when solving logarithmic equations, and that's what we're going to do first. Okay. Now notice when we have a logarithmic equation, of course, there's logs on both sides of the equal sign. What we're saying here is given that C, L, R, all three of these things have to be bigger than 0. Okay. And C, the base, can't be equal to 1. Then what you see is this. If log base C of something called L is equal to log base C of something else called R, well, that just means that the L must equal the R. So as long as you can rewrite a logarithmic equation so that there's one log on the left and one log on the right, then the logs kind of cancel out, so to speak, and then the left side just equals the right side, right? L equals to R. Over here in the box, it says, don't forget about some restrictions on logarithms. Yes, don't forget that log of 0, okay, and also log of some sort of negative number, so a negative number, those are both undefined. So that expression has to be bigger than 0, okay? All right, let's take a look at example number 1, and hopefully with some examples you'll see how we can solve logarithmic equations. Notice 1a here has log base 2 72 equals to log base 2 of the expression 12 plus 2x. So you see how there's one log on the left side, one log on the right side, and they're both the same base? Well, that just means the other stuff, or the 72, must equal to the 12 plus 2x. Yeah, so we just kind of forget the logs, okay? And now we have this lovely equation. We'll just subtract 12 off both sides. That gives us 60, and that equals to 2x. We'll divide both sides by 2, and we get x equals to 30, okay? Now we should always double check. We got to make sure that the number is actually a positive number, not just the answer though, but the number here, the expression. So if I were to plug this back in, 2 times 30 is 60 plus 12, that's 72. Oh yeah, that works. Life is good. Okay. All right. Well, how about the next one? Notice on the left-hand side now, we don't have one logarithm. We have two logarithms here. We have log base 7, 2x plus 2. And we're subtracting from that log base 7, x take away 1. Well, how can we write this as one single logarithm? You guessed it. We're going to use those log laws. And the subtraction is equivalent to, yep, it's division. So how about log base 7? And we'll write this as 2x plus 2 all over x minus 1. And this must equal to log base 7 of x plus 1. So now that I've written it with one log on the left, one log on the right, we can then say the numbers for each parts must equal each other. So this part here must also equal this part there. So I'm going to now say 2x plus 2 over x minus 1 is equal to x plus 1. And now it's time to solve. So you can either cross multiply or whatever you wish, but go ahead now and solve. I'm going to multiply both sides by x minus 1. So now we have 2x plus 2 on the left side, and then on the right hand side we have x plus 1 times x minus 1. Go ahead now and distribute and try to simplify. So we'll continue to do that. Let me just scroll down a little bit. 2x plus 2. And then we'll distribute x squared, I think that's minus x plus x minus 1. I'd like you to move everything to one side. I sense a quadratic coming up here. And the left-hand side must be equal to 0. Squared term, linear term, constant term. That's right. If you like to factor, this is your day. Find me two numbers that multiply to -3 and add to -2. How about -3 and +1? And then go ahead and solve. So make that part equal to 0, therefore x equals to 3. We'll make this part equal to 0, therefore x equals -1. Okay? And don't be so fast in just circling those as your answers. Remember how I said the expressions have to be positive. So what you should do is really check. Okay, so I'm going to go over here and just say what you should do is just check your solutions. Okay, for x equals to 3, if I were to plug it back into my expression, I have log base 7. 2 times 3 is 6 plus 2 is 8. I'm just plugging it back into the original equation right now. Okay, take away log base 7. 3 minus 1, that's 2. And that's supposed to be equal to log base 7, 3 plus 1, that's 4. Okay? Now, notice the numbers inside the brackets are all positive, so I'm thinking this is probably okay. And it is. Right? If I really want to double check, then of course that part just becomes 8 divided by 2. And what's 8 divided by 2? Oh yeah, that's 4. So yeah, this totally works. Okay? Yeah, that's good. So that's an answer for sure. Yay. How about x equals to -1 though? Now this is where we have to be careful. Because if I plugged in -1 into that first expression up here, log base 7, now 2 times -1 is -2 plus 2 is 0. Here's a problem. Now if I keep going, look, log base 7, -1 minus 1, that's -2. Oh, more problems. Oh, log base 7, -1 plus 1, oh yeah, that's 0. Okay. Once again, those restrictions, remember the restrictions. Okay. Log can't be 0, right? Doesn't make sense. Log also can't be negative, so this one doesn't work. Okay. So even though the algebraic solution exists, this is what they call an extraneous root. And we should really ignore it. So the only solution for this one is x equals to 3. Okay. Well, the rest are pretty much the same, but I'm going to let you take a look at this first. I don't want to spoil the fun for you. How about part C? I want you to think about this. What can I do to solve this log question? Two things probably scary here. The left side, there's 2 logarithms. That's scary, but you should know how to do that. And the right side's a number. There is no logarithm. Okay, so go ahead, think about this. First thing, I would, yes, combine at least the left-hand side. Okay, plus means you're going to use the log laws. I think we're going to use the product log law and multiply these together. Okay, so we'll continue to do that. We'll have log 7, this will be x squared, minus 5 plus 1, that's minus 4x, and then take away 5, and this equals to 1. Okay. Now, once you get to this stage, you've got 2 choices. Okay. If you like the idea of, hey, there needs to be a log on the left and a log on the right, then what I'm going to ask you to do is with this method, and I'm going to put here method number 1, convert the number into a logarithm. Meaning this, the left side is still going to be the same because I've got the log. But the right side, I need to rewrite the number 1 as a log with base 7. So think to yourself, 7 to the power of, remember this is 1, right? So 1 is your exponent. So 7 to the power of 1 equals to, yeah, 7. So what I'm really saying to you is log base 7 is equal to 1. So what we've done is we've took the 1. So once again, I take the 1 and I convert it into log base 7. Now, since you have a log on the left and a log on the right, you can apply that rule. And therefore, x squared minus 4x minus 5 must equal to the number 7. And now we've moved everything to one side. We've once again got a nice quadratic. And of course, you can solve by factoring or using the quadratic formula. It's up to you. I like to factor if I can, so find two numbers that multiply to negative 12 and add to negative 4. I think it's 6 and 2. And go ahead and solve. So x just equals to 6. X just equals to negative 2. Okay. Once again, you should go back and check. I'll tell you that when checking, you should check yourself. But I know right away that the negative 2 does not work. And if you're curious why I know right away is if I were to plug this into here, right, x minus 5, negative 2 minus 5, that's negative 7. Logs can't be negative, so I know that one doesn't work. Okay, so you can do all the checking if you want, but I already know this one doesn't work. This one's going to be my extraneous answer. And my only solution, or my only root, is this one. X equals to 6. Okay. Now wait a minute, that was just method number 1. I said there's another method. You're right. So if you didn't like how I took that 1 and I converted it to log base 7, here's another method you can choose. And method number 2 I'll call is this. You've done this before. You see how you have log base 7, some number equals to 1? Well, why don't you just convert this to exponential form? So you can do that really quickly too. So from what you learned in, I think, 8.1, section 8.1, we have this, right? Remember this? I'll write this down for you. Remember this? Y equals log base cx. That became c to the power of y equals to x. So that's what I'm saying here. Convert to exponential form using this. So then the base would be 7. The exponent would be 1. And this equals to x squared minus 4x minus 5. So in a question where there's only one logarithm, you don't really need to convert into two logarithms like in method number 1. You can just use the equivalent form, the exponential form, and do the same thing. Now notice you get the same answer, 7 equals to x squared minus 4x minus 5. Going to move the 7 to the other side, so x squared minus 4x minus 12. Well, look, it's the same, right? So nonetheless, it's the same in the end. You're going to still have to factor. It's up to you which way you like better. Okay? Alright, so D is yours, and yours alone. Now, for D, I want you to make a distinction here. That square only applies to the x plus 1. Okay? So don't get that confused. Don't write this as log x plus 1 all squared. That's not the same. Okay? Not the same in this case. In this case, what you do actually have, okay, what you do actually have is maybe writing it like this might help you out. It's x plus 1 all squared. Okay, so the square only applies to the x plus 1, and then after you've done that, you're taking the logarithm. Alright? Okay, let you try this one whichever way you wish. Okay? There are a few different ways you can do this. It's up to you what you want to do. Okay? You try first. Stop tape. Try it. Yes, I meant it. Stop the tape. Try it. Remember, there's no base, so this is base 10, okay? So the base 10 logarithm must be 100. Log base 10 100 equals to number 2. And then, of course, you're just going to equate the number portion, so x plus 1 squared equals to 100. Going to have to factor. extraneous. There you go, 9 is the answer. Don't like method number 1? You can do method number 2. That's, of course, change into an exponential form. By the way, you don't need to do all these different methods. It's up to you which one you like, okay? But I'm just trying to show you a few. So once again, this is base 10, so this becomes 10 squared equals to x plus 1 squared. That's 100. And then that's x squared plus 2x plus 1. Well, that's the same thing as that, so same. Okay. Ah, you say, is there method number 3? In this case, yes, there is. I think method number 3 is one that you probably did not think of. And I do want to show this to you because I think this helps sometimes. This actually might be the easiest one. Let me rewrite the question again. X plus 1 squared equals to 2. What log rules can I use when there's a exponent or a power? Yeah, I can use the power rule. The power log rule says I can bring the exponent down. So watch as I do this. It's 2 log x plus 1 equals to 2. Okay, well, how do I solve this? I probably want to isolate the log by itself, so I'm going to take this 2 and going to get rid of it. So I'm going to divide both sides by 2. So then I have log x plus 1 equals to 2 divided by 2 is 1. And then now I'm going to change into exponential form. Change into exponential form. And remember, this is base 10, so 10 to the power 1 equals to x plus 1. Well, 10 to the power 1 is just 10. 10 equals x plus 1. Oh yeah, x must be 9. Done. Method 3, probably the easiest of them all. Okay. Hope you've had some good practice now solving log questions. Turn the page, and I'm going to show you something different. What happens when the bases of the logarithms in a logarithmic equation are not the same? See, all the ones I've given you in the past, on page 1, the bases were the same. Now things get interesting. Okay? And once again, just remember how logs are exponents, so the key is to try to rewrite them using the same base. Now here's a question. 3 log base 5 of x minus log base 25 of x equals to 10, and you're trying to solve for x. The problem here is 25 and 5 are not the same base, but you should know, hey, they're related somehow. And I'm thinking 25 I know is just 5 squared, so that's going to factor in somehow in solving this question. You're right. Okay. To help us out, I'm going to ask you to do the following. Okay, it's that log base 25x that's the problem. So let's just look at that right now. Log base 25x. I'm just going to call this a dummy variable. Let's call it a, because I want to see if we can rewrite this using log base 5 instead. Okay, so looking at here, I've got log base 25x equals to a. Let's first of all change into exponential form again. Change into exponential form. So if I do that, it's the base, which is 25, to the power of a, and that equals to x. Now, this is where I can now rewrite the 25 as 5 squared. So it becomes 5 squared with an a equals x. And that just simplifies to 5 to the power of 2a equals to x. Okay, now I want to rewrite this back as a, so I'm going to now go back and change into log form. And when I do that, watch what happens. It becomes log base 5 of x equals to 2a. So notice now I've got a log base 5x. Hey, that's good. Okay, but ultimately I started with a, not 2a. So I think what I'm going to try to do next is just divide both sides by 2. Okay, so that just becomes 1/2 of a log base 5x, and that equals to a. This is very important. Why? Well, because if both of these are equal to a, then that means log base 25x is the same thing now as half log base 5x. And why is that important? Because now I can substitute this into here, and look at this. I've now changed my equation, and instead of having two different bases for the logs, I now have the same base. And this makes life so much easier now. Because you see I have 3 log base 5x's, take away half of a log base 5x. Well, 3 minus a half is just 2.5, so 2.5, or maybe I'll use improper fractions, okay? So 2.5, same thing as 5 over 2, right? 5 over 2 log base 5x equals to 10. Well, I want to isolate the log base 5x. I'm going to divide both sides by 5 over 2. So divide both sides by 5 over 2. So I get log base 5x. Dividing is the same thing as multiplying by the reciprocal, so that's times by 2 over 5. 10 times 2 is 20, divided by 5 is 4. So this just becomes log base 5x equals to 4. And now how do I solve this? Well, once again, you can do whatever you wish. I like to change to exponential form when I only see one logarithm. And we have now 5 to the power of 4 just equals to x. 5 times 5 is 25, times 5 is 125, times 5 is 625. And there you go. There's your answer. Tricky, tricky, but not anymore, because I've shown you how to do it. Hehehe. Okay, let's take a look at one more. I've got, this question here, example number 3. Let's take a look at this one. It says, according to Keebler's law, a mammal's resting metabolic rate, which I call R, in kilocalories per day, is related to its mass, m, in kilograms, by this lovely equation. Log of R equals to log 73.3 plus 0.75 log of the m. So the question is, what would be the mass of the raccoon that has a resting metabolic rate of 925 kilocalories per day? So I guess what they're saying is find m when R equals to 925. Okay? Go for it. Log 925 log 73.3 plus 0.75 log m. Just like algebra, I'm going to try to isolate the thing with a variable, so I'm going to get rid of this log 73.3. So by doing that, I'm going to subtract, so log 925 minus log 73.3 equals to 0.75 log m. What can I do with this? Well, there's plenty of ways you can do this one. Okay, I'm going to just pretend it's like algebra. So the next step I'm going to do now is I'm going to divide by 0.75. So I'm just going to pretend this is just all algebra, which it is, and do it that way, where I'm going to divide by 0.75, and that equals to log base m. Okay, you can calculate that right now if you wish, and maybe I should, just makes it a little bit easier. So log 925, take away log 73.3. Okay, press enter first, do the subtraction first, then divide by 0.75. Okay, 1.4680. 1.4680. Oops, wrong one. Arg. Minimize. 1.4680. 50344. 50344. This equals to log m, Once again, this is log base 10m, so if I want to convert this into exponential form, then yeah, 10 to the power of 1.468050344 is equal to the mass of the raccoon. That, of course, being, calculator time again, 10 to the power of my answer, about 29.4 kilograms. There you go. Now, notice that's just one way of doing it. If you wanted to solve this another way, you could have also just simplified. Simplify the left side into one logarithm. So that's log. Subtraction just becomes, oh yeah, division. So we could have done this. And that 0.75, if you didn't want that, you could move it up into the exponent location. So then, if you do it this way, then of course the logs kind of just cancel out. So you have 92.5 or 925 divided by 73.3 is equal to m to the power of 0.75. So really, you want the 0.75 root of 925 over 73.3. We can do that on your calculator as well. Okay, let's do the 0.75 root. Number 5. I hope this works. 925 divided by 73.3. Same thing. 29.37 or 29.4. Okay. kgs as well. Both ways work. It's up to you what you like. Ta-da.